Hi, let's look at chapter 2 of Understanding Statistics. And in this chapter, we're going to be looking at some basic mathematical and measurement concepts, kind of the tools for doing statistics to lay the groundwork past the definitions that we did in chapter 1 and before we get into the descriptive statistics of the next chapter. Let's let's review with some of the vocabulary we learned in the previous chapter. 30 APU students are randomly chosen in a study of shoe size and gender of APU students. APU, for those who don't know it, is Azusa Pacific University. That's where I teach. The average size for women is 8, and the average size for men is 10. Now I've got some questions here about the vocabulary that we've been looking at. What is the sample? What is the population? What are the variables? And what are the statistics? Okay, now let's look at these. The sample are the 30 students that are randomly chosen for this study. So that's what the sample is. It's a small number of people that we look at. The population, that's everybody that we're interested in. The population is all APU students. This is a study of shoe size and gender of APU students. What are the variables? Well, there's two variables. First of all, there's shoe size. The shoe size was measured for everybody. And then the other variable was gender. People were noted as being male or female. And then the statistics are the two averages that we have. The average shoe size for women is 8, and the average shoe size for men is 10. Those are the two statistics. Now let's move on to some new material. Well, let's start off with some basic mathematical and measurement concepts. And even before talking about that is like, why use math? Most humans don't like math. Why do we do this? Well, it's because it's one of the very best ways that we have for creating and communicating information. For example, if I were teaching an on-the-ground class, I could ask how many students are in the class. And people could say, oh, there's a lot, just the right number. There's a bunch, not too many. Well, that doesn't give us a whole lot of information. If I said there are 17 students in the class, that would provide very precise information. So by counting, we can just do a lot better at communicating exactly what the situation is. Now, this whole idea of metrics or measuring stuff that we're using these math and all these scales and all this measurement for has caused businesses and psychology and all of culture to, well, maybe not all of culture, but an awful lot of many large parts of modern culture to advance enormously in the last few decades. Look at how your grandparents lived when they were born. Cars were rare. Very few people took airplanes. Nobody dreamed of computers. It was just a very simple lifestyle, and all these advances in technology and healthcare and a lot of pedagogy and social services, these advances have been made because people have measured what works. They've looked for relationships between things. They've compared what does work well with what doesn't work well. And so we've been using statistics for all of this. Now, it's interesting that even in the Bible, and since Azusa Pacific's a Christian college, and since I personally hold Christian values, a lot of times we want to kind of make a link to what's in the Bible. We've got the book of Numbers in the Bible. What's the book of Numbers? Well, it's got a lot of numbers. It starts off with a census of God's people in the Old Testament, and it ends with a census of God's people in the Old Testament. So you have lots of numbers, and it was a good use because it showed how God had blessed his people. In the Acts of the Apostles in the New Testament, Luke is often talking about how the church was growing, and it's evident he presented numbers of how many people believed or were baptized or were in the community. That was a good use too. Now, it's interesting that there's also a bad use of numbers. In 1 Chronicles 21, it says that Satan motivated David to take a census of his country, and it displeased God. And we don't have all the details we'd like to there, but apparently there was something in David's motives that were not God honoring, perhaps pride or arrogance or the willingness to trust in the military power rather than in the Lord. But that was an example of using numbers for a bad purpose. So math and numbers are generally a good thing because they allow us to be precise, move forward, measure what's changing and what's related to other things. Now, we're going to talk about some of the shorthand that we use in statistics. We use a bunch of mathematical symbols, and we do that because it's like text abbreviations. We use them so common that we want to just have some shorthand so we don't have to write out an equation with 50 things in it each time. We can just use a symbol that says, add up these 50 things. And if you don't learn some of the basic meaning, some of the basic mathematics, you'll get lost really quickly in statistics. Now, here's some common symbols. We're not going to talk too much about what they mean, but just how to say them because you want to be able to read them. The first one is X bar. That's X with a bar. That usually means the average of whatever X is. We use a lot of subscripts in statistics, and so that's a little number down to the right of the letter. So we can say X1 or X sub 1 for this symbol here, and that means the first X in a series of X's. We could have X14, that would be the 14th X in a series of X's. Then we've got some Greek letters that we use a lot. That little thing that looks kind of like a swimming fish is an alpha. Then we've got beta, which is a B made in one swoop. We've got chi, that looks like X, but it's not. It's really chi. In fact, that's you've heard of the abbreviation for Christmas. A lot of times it's written with an X. It's really written with chi, because in Greek, the word for Christ, Christos, is written with a chi, and so it's just an abbreviation for Christ. We've got phi or phi. You can pronounce it either way. That's like a circle with a line through it. Eta is like a long E in Greek. It looks like an N, but it's really like the letter E. We've got the letter mu, which is an M. It kind of looks like an M if you use like your handwriting, a capital M or something maybe. So it's called mu. Then we've got rho that looks like the letter P, but it's really R. And then we've got two sigmas, and these two sigmas we use all the time. We have the little sigma that looks like a little pumpkin with a handle going out sideways. So that's little sigma. And the big sigma is kind of like this square backwards X. We'll be looking at that shortly. And then the last one that we come across is omega, and that's the last letter in the Greek alphabet. Let's talk more about subscripts. So let's suppose that X stands for some variable that we're measuring, like age. We can say X is a person's age. And if we have a whole bunch of people, we have a whole bunch of ages. And so suppose we have N people, we can indicate whose age is which with the subscripts. So if we say X sub I, that means I is the ith score, where I can be any number from 1 to N. For example, we've got the age of 6 people, and the first person, their age, well, actually, these look like kids specifically. We could call the first kid's age X sub 1, which would be 8. The second kid's age would be X2. She's 10. X3 is the third kid's age. He's 7, and so on. And so we can tell which age belongs to which kid by writing down the subscript next to the X, which we know that is age. So if we got a 7th kid, that would be X sub 7. And then we'd go ask the kid how old he or she is, and she would say, and then we would know X sub 7. So that's the basic notation of subscripts. Now, one of the things that we use all the time are summation formulas, and we're going to just look at how to do them on Excel. You can look in a textbook for some of the details of calculating summations using mathematical formulas, but since this class is focused on Excel, I want to focus on Excel. So This is where we would use the capital sigma if we were handwriting this to indicate the summation. So let's let's take an example of 5 girls who I will use as an illustration several times in this course. They all have they're all named after places in France. And we've got Brittany, Rochelle, Prix, Lorraine, Paris, Paris. And these girls, the thing that they like doing the most is sitting around talking about what they enjoy eating. And one of the things that they enjoy eating the most is frozen burritos. In fact, they recently had a conversation about how many frozen burritos were they able to eat last week, given the budget that they had. And we've got the data here, and we have Brittany, who ate 1 frozen burrito. Rochelle had 1 also. Brie had 2. Lorraine had 3. And Paris had 5 frozen burritos. Now, constantly, we're trying to add these all up. So you would see some summation of x if we wanted to add these all up with a capital sigma followed by x. And we can do this in Excel by any number of a command. Kind of the easiest one. Okay, whoops, let me get back there. Okay, let me enter into Excel here. I'm double clicking on this file and PowerPoint turns into Excel. So let me get it a little bit bigger. Okay. So what we want to do is the Excel formula for adding these together is we can use equals, and then we use the Excel command sum. So we use the equal to tell Excel we want to do some type of calculation, and then we do the sum, and then we do open parentheses, and we start with C8. That's the first number there that lights up, and then we can type in 2 periods or a colon, either one, and we want to add up C8 to C12. So I type in C12 and it says, oh, you want to add that whole row together? And I say, you know it, and I close parentheses, and that gives us a summation of x1, x2, x3, x4, x5. The summation of x is 12. Now if I click in here, we can go up to the formula here, and it says equals sum C8 to C12. So now, suppose we wanted to calculate the number of overcooked corners on these burritos, because you know that's the main problem with burritos when you microwave them, is those corners get awfully hard. So we could calculate the sum of 4x. The way we could do that in Excel is first we need to calculate how many corners each burrito has. So you just multiply that by the number of burritos by 4. Well, each burrito has 4. We want to know how many hard corners each girl ate last week. So we do the equation now inside the table equals 4, and then we're going to do star, and we want 4 times x1, so that would be C8. So 4 times C8, and then we press enter, and we get a little box down here, and it says, do you want to override all the cells in this column with this formula? Yep, we do. And there it calculates the number of corners that each girl ate last week. Now, we want to sum all those up, so we could type in our sum formation, or we can just take the formula here and drag it over to this column, and it will recalculate it based on this column of data. Everything that was in the C column, when it got dragged over to the D column, it changed all those C's to D's and tells us how many corners the girls ate. So 12 times 4 is 48, so it gave us the right number. Now we can do some more complicated summation. We can do the summation of 2x plus 1. Well, why would we want to do the summation of 2x plus 1, you might ask? Well, next week is a special week for these girls. At the supermarket, they're having a 2-for-1 sale on the burritos. So each girl is going to be able to buy twice as many burritos as she bought last week, plus there's a coupon in the newspaper for one free burrito in the little flyer, the news flyer that came in the mail. So for the same price, each girl is going to be able to buy 2 burritos plus get one free. So we want to calculate 2x plus 1 for each girl. Let's go for Brittany. And so we're going to use the Excel formula starting with equals 2, and then we use star for times, and the number of burritos that she normally gets is C8, and then we want to add the free one in, so we do that, and Brittany gets 3. Now we can use the autocorrect options for overwrite all of these, and we see how many burritos everybody gets. Paris gets 11. This is going to be a glorious day for her. And we can add these all up by, once again, dragging the previous formula over here, and it adds up to a total of 29 burritos next week. They only had 12 this week, and they're going to go up to 29 next week. This is a good week for burrito eaters. All right, now let's move on. Whoops. No, I'm trying to get this full screen. Now let's click. Okay, that should help. There we are. Okay. Now let's talk about rounding numbers. That means reducing the numbers of after the decimal point, because when we get walls of numbers, things are not nice. Look at this little Excel spreadsheet here. Here we've got the some characteristic for a group of basketball players. It says that the average shoe size is 12.46378. The average height in inches is 78.30045, and so on. Those are not pretty to look at. There's too many decimal points. And in psychology, in organizational psychology, we have a tradition of rounding everything to 2 decimal points so that it's easier to read. Now, you might be saying, that seems like an arbitrary rule. Well, yeah, it is kind of an arbitrary rule, but that's a tradition, and so that's how you want to report numbers. Now, how do we round numbers in Excel? Let me go into Excel here. I'm going to go into this into the spreadsheet there. And what I can do to round numbers is I can select a whole column numbers that I want to round. So I right-clicked on column D, and now I go up to Excel under the Home tab. I go to General, and I choose Number, and number means rounded to 2 decimal points. So I do that, and it rounds it all to 2 decimal points, and it rounds them correctly. If the number ends in 5, it rounds it up. If it ends in something less than 5, it rounds it down. And so this is how you round numbers in stats in Excel. You go to Home, you select the numbers you want to round, you go to Home, then you go to Number, and then you choose the number formatting. All right, let's choose a different topic now. Let's talk about measurement scales. Now, measurement scales are the way that we go around measuring things. The way that you tell if somebody's male or female is different than how you tell how tall somebody is. And we're going to use different scales for measuring these things. And I'm going to use kind of start off with a shoe theme here. There's 5 measurement scales that we use whenever we measure things having to do with humans, and they can be nominal, ordinal, interval, or ratio. Now, something kind of a nice little mnemonic is that it's spelled N-O-I-R, and that's the French word for black, noir. That's how you can remember what the 4 categories are, noir. So suppose we're just taking everybody's shoes and we're placing them in piles. We can put them basically in categories. And these categories would be how we would classify what's known as nominal data. Nominal pretty much means categories. So we might put all the Nikes in one pile, all the New Balance in one pile, all the Sauconys. I'm pretty sure that's how you say it. I think I looked it up on the website. even though it does look like Saucony and some people say Saucony. Maybe we can call it either one. We could classify them as in nominal data. Now, one of the characteristics of nominal data is that there's no order to it. We don't say that Nike comes before New Balance or New Balance comes after Saucony. They're just groups. We can put the groups in any order and they still make sense. So that's the characteristic of nominal data. There's no order to the groups that we use. Now, in contrast, there's ordinal data. And ordinal data represents an order. You can see the word order in there. So for example, if we had a race and we had the results, person A might come in first, person B second, person C third, person D fourth. And if we knew that, we would know the order of how people finished races. But we wouldn't know if person A was way, way, way ahead of person B, or if B was close to person C. We wouldn't know anything about the distance between them. All we would know about is the order if we just knew that they came in first, second, third, and fourth. So ordinal data has our scales that have an order, but the intervals between points are not defined, and perhaps they're not equal. Now let's go to ratio data. That's a bit different, or we're going to skip interval data, and then we're going to come back to it, go to ratio data. Ratio data has the interval between each number is equal, but it doesn't especially mean that there's a but, and so, well, let me try that again. The interval between each number is equal, and 0 means that there's none of what's being measured. So we suppose we have a thermometer that measures temperature in Kelvin, absolute degrees. That's an interesting unit. If it was 0 degrees, that would be absolute zero. Everything is frozen completely. There's no movement of molecules. It's like absolute, the absolute coldest that you can get. Whereas 300, which is kind of around room temperature, would be 300 notches, 300 degrees above, and we could say that 300 degrees is twice as much as 150 degrees. The atoms are moving twice as fast, or they're having twice as much energy, something like that. Now, in contrast to a ratio data, we've got interval data, where the interval between each number is equal, but the 0 doesn't really mean anything. There's none of what's being, 0 doesn't mean there's none of what's being measured. So if we were measuring people's temperature in Celsius, they might have a temperature of 37 degrees, but that doesn't mean that they're twice as hot as someone that had 18.5 degrees. And if you have a temperature of 0 degrees Celsius, that's 32, you might be frozen, but you still, it doesn't mean you don't have any temperature. You don't have any temperature to you. It's only at minus 273 that you all heat energy completely stops. So let me give another example of ratio data. Ratio data would be how we normally measure things, like how long does it take you to run around a track. If it takes you 8 minutes, that's twice as long as 4 minutes. And if it took you 0 minutes, that would mean it doesn't take you any time. We could do the same thing with weight. If you weigh 200 pounds, that's twice as much as 100 pounds. And if you weigh 0 pounds, that means you don't have any weight. In interval data, like years, the year that you were born, is the distance between each year is an equal interval, but somebody born in the year 2000 is not twice as old or new or anything as someone that's born in the year 1000. You can't do ratios with them. And that's because 0 doesn't mean that someone has no age. In fact, the year 0 didn't even exist. It went from 1 BC to 1 AD. So let's do a little exercise here. Let's imagine you have a whole bunch of Beanie Babies, and we've got a bunch of variables that we could describe with Beanie Babies. We could talk about what type of animal is it? Dog, a cat, a monkey. We could talk about how many arms and legs does the Beanie Baby have. Another variable we can measure is the color of its eyes. We could look at its name. We could look at its copyright date, its weight, or its cuteness. All these are variables that are associated with Beanie Babies. Now the question is, each one of these, are they nominal, ordinal, interval, or ratio? Well, the type of animal is categorical. You've got dogs as a category, bears as a category, cats as a category. So that would be nominal data because you could categorize them according to what type of animal they are. You could do reptiles and mammals. You could all kinds of categories you could use, but there's not necessarily an order associated with whatever categories you choose. So it's a nominal scale. Now, how about the number of arms and legs? Most animals have 4 arms and 4 legs. Well, that's twice as much as 2 arms and 2 legs. And if they have no arms, no legs, like a snake, that means 0 means 0, none of it. So the number of arms and legs would be a ratio scale that we would be using. Now, if we use the color of eyes, black or blue or brown, those are categories. So once again, it's nominal. And the same thing with the name. All the Beanie Babies that are named Chipper, or all the ones that are named Fuzzy, would be each put into a category. So name would be nominal. And in fact, in French, nom, N-O-M, where we get the word nominal, means name. We're grouping them by names. Now, the copyright date, that's interesting. That is interval data, because the distance between 1998 and 1999 is the same as the distance between 1999 and 2000, but 2000 doesn't mean that it's twice as old as 1000. And so, and 0, if it had a copyright date of 0, doesn't mean that it's missing something or has 0 of something. It would mean that it would be very, very, very old if the year 0 had actually existed. Then there's there's copyright. The weight, how much do they weigh? 125 grams, 140 grams, 70 grams. That would be ratio also, because 140 grams would be twice 70 grams. And if something weighed 0 grams, it wouldn't have any weight. And then cuteness. You could rate each one of them on a scale of 0 through 10 on cuteness. We could say, oh, the owl looks like a 7. The cat looks like an 8. The rhinoceros is a 4, and the horse is a 3. Well, what type of scale would that be? Well, it wouldn't be a ratio, because a 10 doesn't mean that it's twice as cute as 5. It would at least be an ordinal, because a 3 is cuter than 2, and a 6 is cuter than a 5. Now, is it an interval? That's a good question. We don't really know exactly what happens in our minds when we classify things. Is the distance between a 2 and a 3 the same as the distance between an 8 and a 9? Maybe, maybe not. So it's a little ambiguous there. We know at least it's ordinal. It might be interval as well. Or it might not be completely interval. It might be approximately interval. So we don't get a real clear answer for cuteness, but we know it's not ratio or nominal. Now let's look at one other aspect of measuring variables. We can divide variables as continuous variables or discrete variables. Continuous variables can take on any value that we want. If we weigh the weight of something, we can say it weighs 180.14 pounds or 180.14325 pounds. We're not limited to just 180 pounds or 181 pounds. Money can be measured as accurately as we want, $55,413.44. And so these are typically ratio scales and interval scales. The nominal and ordinal can't be continuous variables. So those are continuous variables. Now note that if we say something weighs 180 pounds, we can talk about the real limits. What does it mean of 180 pounds if we're measuring to the nearest pound? It means that it can vary from 179.5 pounds to 180.4999999 pounds. Any number there would be rounded to 180 pounds if we were measured to the nearest pound. If it measured to exactly 180.5, then we would round it up to 181. Now, in contrast to continuous variables, there's discrete variables, and those are variables that can only take on certain values. For example, if we had a Likert scale, I like Justin Bieber. How much do you agree with that? 1 is strongly disagree, 5 is strongly agree. You're only allowed to choose 1, 2, 3, 4, or 5. You can't choose 2.7, and you certainly can't choose 2.7634. You can only choose discrete values. Gender is often calculated as a discrete score, 1 or 2 for male or female or male. You can do it in any order you want. Year of birth is often a discrete value. We say someone was born in 1990. We don't ever say they were born in 1990.234. So these discrete variables are typically nominal in interval, but sometimes they can be interval scales also. Yeah. So it's we've got some flexibility there. All right, this concludes our lecture on some of the fundamental mathematical concepts. And in the next chapter, we'll start looking at descriptive statistics.